Again to Flipped Harber for Calculus. In this video we're going to cover section 2.6, tangents, velocities, and other rates of change. Our objectives for this lesson are to find the tangent slopes using limits. And we're going to look at how to find velocities using limits. Our outline for this video, we'll talk again about what secant and tangent lines are. We'll talk about how to find the slope of a tangent line without guessing. We'll take a look at another equation for slope, then we'll move on to instantaneous velocity, and then talk about generic instantaneous rates of change. So let's talk again about what secant and tangent lines are. Secant and tangent lines are lines that go through a function, go through a curve in 2 points, but then tangent lines just touch that curve, just touch that function at 1 point. And remember, this tangent line has the same slope that the curve actually has at that point, and we're actually very interested in the slope of that tangent line. Now I've got here a picture of a function f of x, a few secant lines, and then the tangent line, all kind of working around this a value. You will see this a lot in this lesson. So remember that a is where that tangent line is tangent to the curve. So it's that point where the tangent line touches the curve. Now, when we want to find the slope of a tangent line, we used to just make a list of slopes of secant lines. And remember that the slope of a secant line is equal to a change in y over a change in x. If we're interested in finding the slopes of these blue secant lines, we would take the difference between the point A and then some generic point x. And we would take the change in the y value divided by the change in the x values. Well, now, because we've talked about limits, and you should start to feel a little more comfortable with this idea of a limit, the slope of a tangent line can be found with a limit. As we take this x closer and closer and closer and closer to A, those secant lines turn into tangent lines. So now what we're doing, because we've introduced the idea of limits, is we're taking the limit as that second point gets closer and closer and closer to our first point. They can never actually be the exact same point, but using limits lets us act like they can be the exact same point. So we now have an equation for the slope of the tangent line. Rather than making a table of secant lines and then guessing, we can actually use this equation to find the slope of a tangent line. So this is a really big deal in calculus, being able to find the slope of this tangent line without guessing. Now, let's find the slope of a tangent line to a curve f of x equals the square root of x plus 1 at a particular point, and that point is going to be 3, 2. Now, remember, our a value is an x value, and this is our a value. The a in this example is 3. It's always just the x value for the point that we're interested in. So just try to always remember that that a value, that a in our equations, is the x value that you're given. So I'm going to go ahead and plug everything in to this equation for the slope of a tangent line. F of x, well, that's the function. That just gets plugged in, square root of x plus 1. And the f of a, well, that's f of 3. Well, there's 2 ways to find this. One, I can plug 3 into my function, so f of 3, or, well, shoot, since I gave you the point, it's right there. That is f of a. So now, on the bottom, the x stays x, and I plug in my 3 for the a. Now, I'm all set. We've got to do a little bit of algebra and some magic in order to get this solved. So let me make one little change here. This should be saying as x goes to 3 now, because wherever I saw an a, I put a 3. So now the trick, of quote unquote, the trick for this. Since I see this square root in the top, I multiply the top by the conjugate of the top. So instead of a difference, square root minus 2, it's going to be the square root plus 2. I can only do that if I do it on the bottom as well at the same time. So many of our tricks in math are multiplying by 1, and that's actually what I'm doing here is I'm multiplying by 1. It's just a 1 that is kind of useful, being the conjugate. So when I do this, now, not being lazy, I'm writing my limit out. Now, when I multiply the top together, since it's two conjugates, it creates a difference of squares. So it's going to be x plus 1, that's the square root squared, minus 4. All over. Now, do not multiply this in together. Leave the bottom factored out, and I'm going to tell you to do that 100% of the time. Okay, I very rarely use 100%. I'll quite often say 99.9% of the time. 100% of the time, when you're doing these limits, do not multiply the bottom because we want stuff to cancel. And what's going to cancel is anything that's making my limit go to 0 on the bottom. So I'm just doing a little bit of simplifying on the top, and you can see what's going to cancel on the bottom. And I'm going to get real lazy and I'm not going to bother to write what's in my second set of parentheses there. My x minus 3's cancel. Okay? If you do this right, whatever is going to 0 on the bottom of the fraction will always go away. And what I have left on top is a 1. Now that the x minus 3 is gone from the bottom, I can go ahead and just plug in my 3 for x. So I have 1 on top. I have the square root of 4 because it's x plus 1, but I'm plugging in 3, so square root of 4 plus 2. Well, that's equal to 1/4. I just found the slope of a tangent line. More importantly, what's the really big idea in calculus? I found the slope of a curve. That is huge. We're going to talk about it in terms of being the slope of the tangent line for a while, but eventually we're just going to ask, what's the slope of this curve? What's the slope of this function? Now, this is the slope of this curve. This is the slope of this function at one point. At a different point, that slope's going to be different. I would have to totally redo this calculation. Okay, so now let's look at another equation for the slope. So this is kind of the exact same equation. We've just kind of dressed it up a little bit different, and I really want you to try to use this one rather than the one we just saw. The one that we just saw was a good transition from the idea of a slope, a change in y over a change in x, to this really standard equation that we're going to use a lot in calculus, this h going to 0. This just seems to be the way that all of calculus is taught. Now let's talk about what the heck is this h. Well, if I talk about this bottom secant line and I want to talk about a slope, I go from one point to the next point. The h is my change in x. So this h is a change in the x value. We're using one symbol to signify a difference between two values. So the h is my change in x. Well, if I go from a and I move over an amount h, my second x value is a plus h. And that's what we see plugged in right here. This is my second x value. Okay, we've seen it, we've introduced it. Let's try it out. Let's find the slope of the tangent line to the curve, f of x equals x squared, at the point 2, 4. So again, this is my a value, and actually the 4 is my f of a. So when I plug in to my equation, and again I'm using this new one, this h, I plug in what my a is, it's 2. I plug in my a value, my 2, into the function to get this f of a. So here is the limit that I now need to solve to find the slope of the tangent line at this specific point. So let's go through how to do this. Because I have a quadratic, because I have a polynomial, there's no real trick to this. What I want to do is just go ahead and square out that binomial. Now 2 plus h squared is not 4 plus h squared. It is 4 plus 4h plus h squared. Okay, I have to FOIL out that binomial. Minus my 4 all over h. Now here's the magic that's going to happen. If I look in the top, I want to be able to get rid of everything that does not have an h. If it has an h, it can stay. If it does not have an h, it needs to leave the party right away. So there's no trickery in this. 4 at the front minus 4 at the back, those go away. Now I can cancel my h's throughout. I'm still using the limit. I haven't calculated the limit yet, so I'm going to not be lazy. I'm not going to stop writing it all of a sudden. I'm going to cancel an h everywhere. So now I have the limit as h goes to 0 of 4 plus h. Now that I got rid of that h on the bottom, now I can go ahead and just plug in my 0. 4 plus 0 is 4. I just found the slope of f of x equals x squared at the point 2, 4. I just found the slope of a curve. Now that's, the slope, one value at one point. If I go to a different point, it's going to be a different slope. Okay, let's talk about instantaneous velocity. Velocity is a slope. It's the slope of a position versus time graph. We use this fact in physics, all the time. Okay, there are all these relationships where one quantity is the slope of another one. So when we're asked to find an instantaneous velocity, we're doing the slope of a tangent line. Now, in order to do this, we need a position equation to find the velocity. So I'm just going to use a really simple position equation, and this is one that you need to know. You just need to know this offhand, that if you drop an object, if you go to the top of a building and you drop a stone, don't do this, you might hurt somebody, but if you drop a stone off of a building, it is going to fall at a very predictable rate because gravity affects every object the same. So our position equation for falling objects, we usually use this S for position. I don't know why. They just didn't want to use P for position, I guess. It's a function of t, it's a function of time, and it's equal to 4.9 times t squared. Now this is a really simple equation for just dropping an object, and it tells us how far it's fallen at any given time. If we have a more complicated motion, something is thrown horizontally or something is thrown off of a building, it's not going to be this simple of an equation. But for objects that are dropped, this is our equation, and we're expected to know that. So we're going to find how fast something is falling after 2 seconds. What we're finding is the velocity, the instantaneous velocity of this object. It's a slope calculation. It's a limit as h goes to 0 calculation. So I've set up my slope calculation. I have f of, now my a value is 2 because I'm looking at how fast is it falling after 2 seconds. So that's my a value. I'm going to have to plug that 2 plus h into my function. I'm going to have to plug that 2 into the function to find f of 2. So when I plug the 2 plus h in, it's 4.9 times 2 plus h squared. When I plug 2 into the function, 4.9 times 2 squared is 19.6. So now there's no real trickery to this one. It's just a polynomial. I am going to take my limit. Don't get lazy and stop writing this. I'm going to leave my 4.9 sitting out there right now, and I am going to FOIL the 2 plus h. Now, I FOILed something very similar to this already. There we go. Still have this minus 19.6 at the end, all over h. Now, what needs to happen is anything that does not have an h needs to go away. Well, this isn't that bad of math. I can do this without a calculator even. 4.9 times 4 is 19.6. That needs to get out of the pool. But this plus 19.h, that can stay. It's got an h. The plus 4.9 h squared, that can stay. It's got an h. This minus 19.6, that has to go. And sure enough, they get rid of each other. I can cancel my h's top and bottom, so I have the limit as h goes to 0 of 19.6 plus 4.9 h. My pen isn't writing real good. That's a 4.9. Now that I've got rid of the h on the bottom, I can go ahead, plug in my 0, and I get 19.6. Now, I didn't really talk about this. The units for this equation are meters for distance, seconds for time. So since this is a velocity, this is in meters per second. So that is how fast that object is going exactly 2 seconds after it was dropped. If I redo this calculation for a different time, I will get a different instantaneous velocity. If I do this calculation at an earlier time, it's going to be going slower. If I redo this calculation at a later time, it's going to be faster because this object is speeding up as it falls down. Okay, so let's just talk about instantaneous rates of change generically, just as a whole. An average rate of change, well, that's just a slope calculation, a change in the y value divided by the change in the x value. Or if we've got everything as a function, it's f of x sub 2, the second x value, minus f of x1, that's our change in y, and the bottom is x2 minus x1, our change in x. So any instantaneous rate of change, what we're looking to do is get that x2 moved in as close as mathematically possible to that x1. And the best way to do that now is with a limit, where we take x2 going to x1. So these are all slope calculations, whether they call it a slope, whether they call it a velocity, whether they call it some other rate of change. These are all slope calculations. Change in y over change in x. But we're taking this limit as x sub 2 goes to x sub 1. Okay, that should be it. Oh, I have one more example. Let's find the slope of the tangent line to the curve f of x equals x plus 1 over x at the point 3, 4/3. So again, the a value is my 3. So to get that 4/3, I plugged 3 into the fraction. 3 plus 1 is 4 on top. Plug 3 into the bottom. So my f of a, my f of 3 is 4/3. So again, I would prefer that you use this limit as h goes to 0 equation. It's just the more generic one that we're going to use so much more later. So try to get used to using that. So I'm using the limit as h goes to 0, f of 3 plus h, again my a value is 3, minus f of 3, and you see it plugged in. So now I have to do the algebra to make the magic happen. And really the reason I'm doing this is to show you the trick that you should use when you have these little fractions up on top. When you see little fractions, the way that we're going to deal with this is we're going to multiply by a common denominator. So I'm going to multiply by 3 plus h, and I'm going to multiply by 3. Now that's going to get rid of my little fractions on top. That's a great thing to do, but I need to do it top and bottom. So multiply by 3 plus h and multiply by 3 on the bottom. This is equal to the limit as h goes to 0. Don't get lazy and stop writing that until you've actually used it. Now my 3 plus h will cancel out, but that fraction is still going to be multiplied by the 3. So I'll have 9 plus 3h plus 3. When I multiply the 4/3 by the 3 will cancel, but it is still going to be multiplied by the 3 plus h. Don't forget about this minus right here. That minus gets carried through. So I'll have minus 12 minus 4h. All over, and remember I said 100% of the time, do not multiply the bottom together. That is a tip from me to you. It is going to be easier if you don't multiply them together. Just let them sit like that. Okay, now I need to get everything without an h out of the party on the top. So I have 9 plus 3 minus 12. Well, again, those just add and subtract right away. The 3h minus 4h, they can stick around. Whatever they need to do, go ahead, let them do it. They're going to join up, and they're going to make a minus h on top. And I still have my h, my 3 plus h, and my 3 on the bottom. This, one of the reasons we don't multiply through on the bottom, when it's factored out, it's easier to see what will cancel. This h will cancel with this h. I'm going to write this one more time with the limit, and then I'll be able to plug in my 0 for h. So on the top of the fraction, I have minus 1, negative 1. On the bottom, I have 3 plus h times 3. Now I'm plugging in 0 for h. So if I plug in 0 for h, 3 plus 0 is 3. Multiply by the 3, I get a negative 1 over 9. So one more example, one more trick that you need to know how to do when you have little fractions. Multiply by the common denominator. And now I'm all done. Time for you to try some of these. I'll see you in class, and I'll see you online.